a Martian habitat. So some background about the about this assignment is we're still talking about material science, and so we're going to try to understand how a material scientist thinks and works, as well as the engineers associated with that in terms of deciding on what materials to use for different applications. Right, so what you're going to be able to do is by the end of the couple assignments here, you should be able to describe different types of materials and their common usages in product design. Right, so some of those we mentioned already here. And then we'll also list material properties that are important to design, including mechanical, chemical, electrical, and magnetic properties. And some of these we talked about before the break. I will go into a little more detail now. All right, so when you're and even from some of your research that you guys did, some of you guys noticed that there are some of these ideas that came up and probably came up multiple times. And if you weren't sure what they were, here's kind of a quick breakdown. So things like coefficient of thermal expansion, knowing that as things heat up, they typically expand or get larger. As they get colder, they tend to shrink or condense themselves. And so the coefficient is saying how quickly does a material change based on temperature. And so we talked a little bit about density before. That's the measure of mass compared to volume. Ductility is really how much can it stretch without breaking. Okay, so that's oftentimes really important. A couple of you guys mentioned things, for example, like memory wire. A couple of you guys researched that. That has a high ductility. It can stretch quite a bit before breaking. You have your electrical conductivity. Right, for some of you guys, you did research on graphene, for example. That one has high electrical conductivity. It allows electrons to move really easily. The opposite of that is electrical resistivity. So that's saying how much does it keep it from moving electrons. Right, you have your fracture toughness. How much resistance does it have of cracking? There's the hardness test. How much does it deform? Indentation, penetration on the surface. Your melting point, at what temperature does it melt? Your shear modulus, how much can it twist compared to, so it's kind of the ratio of shear stress compared to strain. So that's a really important one when it comes to material strength. You have your specific heat, so that's kind of, and thermal conductivity. These are temperature related. Toughness, we kind of mentioned this a little bit already. You have your tensile strength, how much can it, with the tension force, how much can it handle before breaking? Yield strength and modulus of elasticity, you can read up on those. There's a bunch here, right? So as you kind of understand these different materials, what you're going to be asked to do is start thinking about if we were to, which we currently are planning for, start sending people to Mars. Right now, as you probably have heard in the news, we have a Mars rover there currently. There's actually a few, but the most recent one is the Perseverance, which is actually landed just in February. So it's been there for a little over a month and a half now, somewhere in that range. And so in preparation for that, we'll do some, I'll talk about the assignment a little bit more, but here's kind of imagining what Mars would look like in the future as we possibly start trying to put people on Mars. All right, so give this a watch with me.
Follow the link below to start your free trial today. Since before the beginning of the space race, people have looked up at the stars and wondered what it would be like to live on other planets. The more optimistic among us have long held that humans are destined to become a multiplanetary species, and maybe they're right, despite the big problems we face on our current planet, which is vastly better suited to supporting life. The prime candidate for a second home planet is Mars, though Venus is also enticing. A handful of eccentric visionaries like Elon Musk have even gone so far as to develop semi-concrete plans of how to build a functional permanent colony on Mars. Whether you think this kind of plan is likely to succeed or not, the idea of a large Martian colony is fascinating. In this episode, we're going to consider what it would take to sustain a colony of 1 million people. First, let's compare specs on our two planets. Despite their obvious differences, the red planet and the blue planet do have some things in common. For example, thanks to their similar rotation speed, one day on Mars is only about 44 minutes longer than a day on Earth. The red planet's axial tilt is also very similar to Earth, at about 25 degrees to our planet's 23. This means that Mars undergoes similar seasonal and temperature variations. Both are rocky planets with metallic cores and similar mineral composition. They have similar surface structures, including mountains, canyons, and deserts. But the differences between the two planets are much more significant than what they have in common. Perhaps the most significant is the Martian atmosphere. Unlike on Earth, the atmosphere on Mars is very thin, only measuring about 1% of the Earth's atmospheric pressure and completely unbreathable for humans. It's composed of about 96% CO2, 2% argon, and 2% nitrogen, with trace amounts of oxygen and water vapor. This stark contrast leads to another. Mars is drastically colder than Earth, averaging negative 46 degrees Celsius, with brutal lows of minus 143 in the winter and highs of 35 degrees Celsius in the summer on the equator. Mars is also very dry and dusty, and is buffeted by frequent sandstorms. The planet also lacks any reasonably sized magnetosphere. What little remains of its magnetic shield measure between 16 and 40 times weaker than Earth's, which leaves Mars susceptible to harmful cosmic rays. Gravity clocks in at about 37% that of Earth, which would be a small challenge to overcome, but nothing compared to the temperature and lack of atmosphere. One final problem is the lack of liquid water. Mars does have water at the poles, but it's mostly frozen and nowhere near the amount we have on Earth. Any successful Martian colony would have to contend with these big problems, and fight to establish any kind of hospitable environment on what should be considered a world hostile to life. So let's tackle those challenges. The first big one would be setting up a habitat that could support large numbers of humans, protect them from the cold and frequent dust storms, provide breathable air, safe drinking water, a way to produce food, and a shield against lethal cosmic rays. No big deal, right? Step 1 would be a large enclosure to act as a central hub for our 1 million Martian colonists. This has often been envisioned as a city beneath a big glass dome, providing light but also protection from the elements. Elon Musk has also speculated that this could be a good formula for his Mars colony, saying that a pressurized glass dome with parks and plant life could be a very pleasant way to live during the long process of terraforming Mars into a more hospitable home. But in order to have a functional colony beneath this utopian dome, you'd need a way to power it. The current frontrunners for powering a Mars base are solar and nuclear, depending on who you ask. Solar obviously comes without the risk of accidental irradiation, but it will require a lot of land area for solar farms. That shouldn't matter though, since Mars is currently nothing but open land and the colony will be fairly small. The settlement would also need large energy storage units for the frequent periods of darkness caused by violent dust storms, which could also damage the solar panels. Assuming we get the power working, the next critical step would be food and water production. In theory, food would be easy enough as long as the colony has access to plenty of water. We have very advanced and highly productive hydroponic farms here on Earth, and there's no reason we couldn't do the same thing on Mars. You don't even need natural light or soil, so the farms could very easily be built underground for saving space and added protection. It's likely that a Martian colonist would have to be okay with synthetic meat or an entirely plant-based diet, because shuttling livestock to Mars might prove to be a bit too challenging, not to mention the added complexity of keeping large numbers of animals healthy and fed. Establishing a secure and consistent source of oxygen and water is probably the biggest hurdle in building a colony on a largely airless, waterless world. One proposed solution is to extract carbon dioxide from the atmosphere and split the molecules into carbon and oxygen. It would certainly be easier to make an automated atmospheric CO2 extraction system than a fully autonomous mining rig with excavators and complex equipment to pull CO2 from the soil. But that is another option. As for water, NASA is currently investigating the possibility of extracting water from underground reservoirs and using highly efficient recycling methods to reduce the overall demand for fresh water. Whether there's enough subsurface water on Mars remains to be seen, but another option would be sourcing ice from the poles, which could be processed into clean, usable water. To make a long story short, we'd have to look at Mars as the British did the Americas, which comes with its own set of ethical concerns, but that's another topic entirely. We could supply the initial and essential components to jumpstart a small outpost, but in order to scale up to include 1 million people, the Martian colony would have to become completely self-sufficient. It would have to make use of the materials within the Martian environment, because relying on shipments from Earth would be both incredibly expensive and very dangerous. If the colony had no way to produce its own oxygen, for example, and something went wrong with the shipment from Earth, there would be a very real risk of all the colonists dying. The proposed solution here is to develop technologies that work with the Martian environment instead of fighting against it. We've already seen promising proposals for methods of making building materials from Martian soil, such as a process called molten regolith electrolysis, which is a fancy term for using electricity to break down silicates into their base components in a single step. This has the dual benefit of creating a metallic alloy that can be used for construction while simultaneously releasing oxygen that can be harnessed for life support systems. All of these things are critical to establish a successful colony on Mars. But the most important aspect is the colonists themselves. We'll need scientists and technical experts, but we'll also need normal people with a knack for fixing things. People who can think on their feet when something goes wrong, find a new way to use an existing tool, think creatively in order to make Martian life more meaningful. Those are areas where humans excel. We've got a long way to go before the technology is ready, but our species has been prepared for a long time. If you'd like to learn more about the daunting challenge of preparing for a Mars colony, I highly recommend you check out Packing for Mars on CuriosityStream. It's a fascinating documentary that highlights just how carefully we have to plan our Mars mission before humans ever set foot on the Red Planet. If you watch my videos, you'll know that I'm a big fan of CuriosityStream. It's an online streaming service with thousands of nonfiction titles from some of the best filmmakers in the game. You can find tons of great episodes like Packing for Mars, and they've got a bunch of material on technology and outer space, which are some of my favorites. Their giant catalog includes content on science, nature, astronomy, technology, and lifestyle, among others. Unlimited access starts at just $2.99 a month, and as a special offer just for you guys, you can get a free trial by following the link below. CuriosityStream is available on just about every platform you can imagine. So wherever you are, you'll always have access to great, interesting content. As an added bonus, your CuriosityStream subscription now comes with a free Nebula subscription.
All right, I'll pause that there. If you're interested in more there, obviously you can keep listening and take a look at those other options. Now, one other video I wanted to show you guys before we get into your assignment is how we would probably start building on Mars. So watch this one with me as well, and then we'll start getting into our assignment here. All right, one more video.
Space travel ignites imagination, but the idea of actually living on other planets has always felt pretty far-fetched. Until now. Faced with unprecedented challenges here on Earth, NASA are exploring ways to actually build on Mars. But how would we get to this planet, let alone build there? This incredible proposal holds many of the answers, along with some lessons for building right here on our own planet. Mars is our closest habitable planet, and taking a manned mission there is seen by experts as our next achievable goal in space exploration. A human presence on Mars would enable us to learn more about the universe, gain a better understanding of our own planet, and search for extraterrestrial life. In recent years, encouraging progress has been made towards this goal, both by NASA and by other organisations such as SpaceX and the European Space Agency. But reaching the Red Planet and building the environments that are essential for any manned voyage there is an extreme undertaking. To help, NASA invited teams of innovators to submit ideas, stipulating that designs must include 3D printing technology that would use the harsh Martian terrain or regolith as a building material for the base. One of the leading ideas is this unique human-centric habitation concept that was submitted by international design practice Hassel in partnership with engineering firm Eckersley O'Callaghan. Here, our future settlers would thrive rather than simply survive. To learn more about the plans and how they would actually work in practice, I met Xavier de Kesteler, Head of Design, Technology and Innovation at Hassel, who masterminded the concept.
We're here at the Design Museum in London at the Mars exhibition. I mean, what is this? How did it come about?
Well, this is an exhibition. It's called Moving to Mars. It's all about how humans will move to Mars, but from a design perspective. We've been working with lots of scientists and engineers to make sure that our design is not just science fiction. It's actually pretty realistic. We only use technology that is existing today or will become very mature in probably the next 5 or 10 years.
Building a settlement like this, in a place where no human has ever been before, is a serious challenge. As each kilogram of equipment is expected to be hugely expensive to transport to Mars, NASA's preferred strategy is for structures to be 3D printed using material from the local environment.
Earth has this beautiful magnetic sphere that protects us from solar and cosmic radiation. Mars is magnetically dead. So which means all the radiation hits the planet and will hit our astronauts. The way you protect yourself from radiation is using a lot of mass. So the ideal thing would be going into a cave. So what we're doing is we're creating our own cave.
Working from London and San Francisco, Hassel developed an external shell which could be made entirely from Martian soil by autonomous robots equipped with advanced cameras and sensors.
We're actually looking at designing specific types of robots to do this task. If we get a robot over to Mars, what might happen if one of two of them fail, there it is, you can't get a replacement part. So what we do, we're sending loads of small robots that kind of work together in building this structure. Think of it like this, an ant's nest, right? They build the ant's nest. If I would take half of the ants away, the ant's nest would still get built. Maybe a bit slower. Same thing here. If not all our robots arrive on Mars, they'll still be able to get built. It will take just a bit longer.
So what's the next step? I mean, robots have made it to Mars. They've built these cave structures for us. At what point do humans go there, and what part do they play?
Well, it'll take a few years before the shell structure is built. Then the astronauts will come. They will also bring their habitat pods. So they'll bring these kind of inflatable structures. Because remember, going to Mars, you're not going to bring heavy stuff or big stuff with you. So we're going to bring inflatable, collapsible structures with us, and those will be inflated, and those will actually have the atmosphere and the pressurized environment that the astronauts will live in.
With the build phase complete, the robots would take on new roles, such as scouting for new locations.
So I mean, the way this proposal's been brought to life is just amazing. What kind of software did you use for animations and graphics and things?
What we've done, we actually worked with Epic Games and Unreal to create this real-time environment. So what you see here in the back of us is a real-time environment showing life on Mars through a whole 24 hours. We've speeded up a little bit because it would take too long, but you'll see it goes day and night and so forth. All done by a company called Lightfield in real time with Unreal Engine. And it helped us also to kind of make really tiny adjustments all the time. So we were able to kind of move the robots, change the lighting, because we were working until such a kind of tight deadline, we had to be able to kind of use the real-time engine to be able to do that.
The environments that many of us associate with space travel tend to favour functionality above all else, prioritising performance and equipment efficiency over human amenities. But Hassel's design turns this convention around and creates a habitat where the crew can live and work in comfort and safety in familiar surroundings, without sacrificing the essential practical elements that a Mars base requires.
What we have here is our rack system. They're all identical in shape, but the infill is always slightly different. Okay. Right? So let's go into, for example, the lab one. And what I can do, I can open it up. I can just now step into my lab, do the experiments. On the left here I have a workshop with 3D printer, even a sewing machine if we need to fix stuff. And once it's all done, I can close it up again and use other parts of the habitat.
The astronauts will be able to repurpose as much waste material as possible, from 3D printing spare parts and tools to making clothes out of landing parachutes.
Imagine the astronauts, they were having lots of waste plastics and waste material from food packaging, from science experiments. So we're thinking to reuse that and recycle it and use that to 3D print furniture.
I mean, it looks really stylish as well. It doesn't look like furniture that's been 3D printed by a robot. It actually looks quite appealing.
Well, it's been designed by a friend of ours, Manuel Jimenez Garcia, and it's printed in his factory in Spain. So we actually used recycled plastics, and all of these are 3D printed and designed specifically for the 3D printing process.
What have you learned from this that can be applied back home?
I've learned a lot about circular economy and sustainability doing this project. And you might think, well, designing something on Mars, that's not sustainable. That might not be on its own sustainable. To be able to survive and thrive in an environment like that, we have to think about sustainability on every single level. That way you really start thinking on how precious really our own environment is, how precious our own Earth is.
So I mean, this has got to be one of the coolest projects I've ever come across. What's it been like to work on it?
It's been really interesting, right? Especially as an architect, designing a really technical space. I hope it actually shows when you compare this space to, for example, the International Space Station, that's purely done by engineers, that it really shows the skill and the need for architects to be involved in really complicated engineering projects as well. As a designer, be just brave and realize that our skill is really necessary and needed in a whole range of different types of projects.
While many technological, financial and political challenges must be overcome before the first manned mission to Mars, this remarkable concept, brought to life in such a compelling way, makes the prospect seem much more feasible. If you enjoyed this video,
All right, so hopefully that set the stage. I'll show you guys a couple of these other videos a little bit later. But for right now, let's go ahead and talk about your assignments here, and I'll give you guys the last chunk of time to get started on it. Like I said, you'll have time next class as well as to work on it. So don't worry if you're not able to get it finished by the end of the block here. But I'll go through the assignment itself. So the idea here is that if we're planning on going to Mars and starting to colonize Mars, we have to start thinking about several things in terms of what things we would need there, as well as what materials we would try to use. Okay, so if you follow along with me here, I'm now in 2.3.2, evidence number 1, and we're in the material selection phase. All right, so when you first open up the assignment, you'll notice that it's a spreadsheet, and there's a few tabs along the bottom. Let me go ahead and open this up in a new window so it's a little easier to work with. Okay, so for the first tab, what you'll be doing is responding and justifying these 3 categories, right? So category number 1, here it is space gloves. Okay, so let's say if you're trying to prepare some new gloves for space, here are some of the things that you want it to happen or for it to be properly functional. Is it needs to have a nice outer layer and a thermal micromaterialoid garment of a space glove that will meet the following criteria. Okay, so it needs to be lightweight and flexible. It needs to insulate the wearer and prevent heat loss. It should shield the wearer from harmful solar radiation. And it should also protect the wearer from micrometeoroids, which could puncture the glove and depressurize the spacesuit. So meaning it needs to be pretty strong and tough without puncturing a hole through the glove. Okay, so the first thing is looking at the material parameters that the engineer should use to compare for different material options. So what you should do for the first section is on the tab on the bottom, there's this material properties chart. This is kind of what I showed you guys a little earlier. What I want you guys to do is start looking at this list and what are the things that the engineer needs to keep in mind as they design a space glove, right? So looking over this list, for example, let's start off with being lightweight, right? So if it's lightweight, then obviously it needs to be, not heavy. So the most thing that probably the best part is this density idea, right? We want it to be mass density, mass per unit volume. It should be low mass per unit volume, right? So for example, just to kind of get you started, I would probably say the first one, be lightweight. Well, in order for it to be lightweight, the engineer should look at the density. It should be a low density material. All right, and then for these other ones, I want you guys to start thinking about, all right, if I want to insulate the wearer, prevent heat loss, which one of these material properties would you be interested in talking about heat? Okay, and specifically heat loss. So you again look through this. What kind of properties would you be interested in order to choose a good material? Okay, so from there you'll kind of do the same thing, except now let's say if you wanted to design a racing bicycle, we want it to be faster and lighter. If we want it to be lightweight, strong and impact resistant, corrosion resistant, low cost, which material would you choose out of this list? Right, you have 4 materials listed here. So based on which one you choose, you need to justify why you chose that material. Okay? And like I said, if you're unsure about what some of these material properties are, look over this chart on the second tab there. That should get you figured out what you need to do. Okay, and then the last one on this page is the living hinge. So living hinge is talking about on this flask is this little tab right here. Typically a living hinge, you want it to be flexible, right? So some of you guys maybe have a water bottle that has something like this. It keeps the cap and the hinge attached, or sorry, I should say the hinge keeps the cap attached to the bottle. So think about what the best material would be that allows it to bend at this small radius without failing, so without cracking or breaking apart. Right, so which one of those materials would be the best based on this kind of design? Okay. Any questions on this first tab? Okay. Now the second thing, hopefully you could probably get this done before the end of class since we still have about 20 minutes. Now the other portion is if you come over here onto the yellow tab, it says Martian habitat diagram. Okay, so for this last part, similar idea to what we did in that first tab. But what I want you guys to do for this one is imagine that you're, again, an engineer and you want to look at the materials that are available on the planet. And so that, you know, as we get the planet ready for people to come, a lot of those materials don't need to be transported, but it's already available there. Right, so what you're going to do is read each material properties. You're going to essentially choose the appropriate material for each habitat component. And so if you come down here to the bottom, you can only use each material for one component of the habitat. All right, so meaning that you're going to go through here, come down, and you have, you know, component number one is the exterior shields, right? So if you remember, in those videos, they talked about, hey, the shield over the entire structure needs to be really strong because, you know, Mars is known to have really heavy winds. There might be debris flying around. So it needs to be able to handle all that. So keeping that in mind, what material would you try to choose? Well, the Martian material list is this other tab down here. So when you click on this, you'll see that there is a bunch of materials, right? And we're going to try to minimize using material twice, right? So first off, you'll kind of go through here and choose which one would you want. So let's say, for example, get you started the exterior shields, right? One of the big things that I would want to keep in mind is that it needs to protect against micrometeorite impacts, right? So that's probably the number one factor. So I want something that's that won't puncture easily and it won't crack easily. For example, if I come here over to material list, one of the big ones might be fracture toughness, right? So I want it to be really fracture tough. And so as I go down this list, I notice that the range of these is pretty high. And we probably want one that's even on the low end would be pretty high, right? So I see, for example, Esperanzal. I don't know how to say some of these words myself, right? So Esperanzal, let's say, that one has a high fracture toughness, right? It says 62 to 150, and that's in megapascals times meters rooted. Okay, so that looks like that might be one of the highest ones. So that's probably my first choice would be this Esperanzal. I also noticed that, you know, Curiosium is pretty high, is 50 to 60. Adirondatum is not bad either, right? So I might jot down a few of these. That would be probably my first choice for the exterior shields. Rationale, again, I'm choosing high fracture toughness. Material number two, similar idea. It's also high in fracture toughness, right? But oftentimes you want to look at more than just one thing, right? Just because it's has high fracture toughness, we also want it to, for example, have high yield strength, right? For example, right? So this one, I noticed that it's maybe not as high as the Curiosium. Okay. Again, so you're going to kind of choose yourself. There's not necessarily one right answer. There's some that might be better than others. The key thing is backing it up with the rationale. Okay, so based on those three, choose your final material choice. Which one do you think would be the best for each of those components? And like I said, you should only have each material once. So the way I would personally recommend this is go through the 3 possibilities first for all of them. And then as you go through them, you're going to choose one. And so that way, if you used one for the exterior shields, for example, then you need to use a different material for the windows, for the doors, so on and so forth. Okay, any questions on your assignment here? Okay, sounds good. When you're all done, like it says in the final step here, I would highly recommend take a screenshot of this and have it available for next class. Again, we'll have some time to work on this next class as well, so don't worry too much if you aren't able to get this done. But you have about 17 minutes now, so hopefully that's enough time to get started. I would recommend, again, start with this first tab, comparing material properties. Okay, jot down your 3 responses and a justification. And then if you still have some time, go ahead and get started on the Martian habitat diagram, and we'll pick up from here next class. Okay. All right, if you have any questions, like I said, please let me know. And besides that, you guys can get started. And if you need anything also during asynchronous time tomorrow, feel free to stop in. You can come in with any questions. Okay, good luck, everyone.